So good afternoon, my name is Carla Ferreira. I'm a PhD student at the Instituto Superior Técnico of Lisbon University. This work is was already presented. Oh, sorry. It's based on multiple monitoring as a defect detection method for quality control of aluminum alloys parts produced by powder bed fusion. This work was also done in a partnership with Polytechnic of the University of Setúbal and our company under the scope of our next Portugal project. So this is the outline of my presentation. I'm going to do a short brief regarding powder bed fusion technology and the defects resulted from the process. Then we'll take a quick look to the potential of micro-CT tomography and melt pool monitoring in improving quality control of AM-produced parts. So the main goals of this work is to produce dog-bone specimens with varying scan speeds so we can induce different types of defects, namely keyhole defects and leg coefficient defects. Then we aim to correlate these defects with the emissions retrieved from melt pool monitoring systems and to try to incorporate these emissions with information retrieved from micro-CT tomography analysis. With this, we propose a methodology in order to enhance the detect and identification of defects in powder bed fusion processes, so we can have probably or not a reliable base fail assessment of the suitability of a given component produced with AM in the industry, for the industry. So I'm not going to take much time with this because I think we already heard about this. We have powder bed fusion being applied in several sectors, for instance, in the aerospace and biomedical industries, but we still have some problems, though, regarding the defects that are produced with this process. For instance, we have hydrogen porosity, which is a material-related defect, but it's of lower dimensions. And when we use, for instance, fixing parameters, we can vary scan speed and induce keyhole defects which are related to low scan speeds, giving too much energy to the melt pool and thus evaporating material, which generates that type of defects with up to 200 microns of diameter. And on the other hand, if we increase too much the scan speed, we are not providing enough energy to the melt pool to molten the material, and we can induce the coefficient defects. So we use the Reis machine to print our samples. Here you can see our printing layout. We have several samples printed with 3 different thicknesses. We based our first approach on the 3 millimeter thicknesses, and we used the meander strategy, which is basically the scan doing this path. And we have a 67 edge increment between layers. This is important because the layers will be turned apart 67 degrees from each other. So in order to induce different defects for analysis, we only change the scanning speed by 30% when compared, when compared to the optimal parameters suggested by the manufacturer. And for micro-CT analysis, we used Worth tomoscope machine, computer tomography equipment, with a maximum error of 4.5 micrometers. And in this analysis, not to take too much time, we only use a resolution of 10 micrometers and a filter of 8 voxel. We also use volume graphic VG Studio to conduct our analysis. Regarding melt pool monitoring systems, we used InfiniIM provided by Reis. This system is capable of capturing the thermal emissions during the melt pool monitoring, during the manufacturing process by using 2 photodiodes, namely the melt pool photodiode, which captures lower emissions. So it is better to check, to use it to check for leg coefficient types of defects. And we can use the plasma photodiodes with higher emissions, which capture higher emissions, to check for keyhole types of defects. Okay. So this is the information we can retrieve from melt pool monitoring system. In this case, the InfiniIM system. We can further analyze this information using InfiniIM Spectral for micro level details, or we can use MATLAB scripts to study in a micro level, which can be useful to detect any a relation between defects and emissions. So regarding our experimental results, basically I'm going to present the 3 mm thickness specimens. This one was the one printed with lower scan speeds. We termed keyhole due to the relation to the defect. As you can see, this only resulted in low amount of defects in the specimen. These are images from the micro CT. When we further increase the speed, we can see that the amount and size of the number of defects and the amount of defects are increasing. Here we have the defects found along the fracture zone. And if we keep further increasing the scan speed, we'll induce several irregular defects ranging from a wide range of volumes across the specimen. Okay. Here you can see the information filtered for higher volumes. And as you can see, we have bigger defects than the other ones and a lot of irregular defects. We can also take from micro-CT 3 important factors, such as sphericity, compactness, and bonding box factor. This is basically an aspect ratio. And we can use this as a criteria to classify defects as spherical or irregular. This can be interesting for further implementation in a machine learning model, for instance. From this analysis, we concluded that the keyhole specimen only produced high sphericity compactness with high bonding box factor defects. But when we increase the scanning speed, we start to increase the size, the number of defects, and decrease the sphericity compactness and the aspect ratio of defects. As you can see, we have the extreme case of lack of fusion sample, which produced a lot of lack of fusions in this sector of analysis. Sorry. Based on this, we proposed a methodology. So we could correlate the emissions captured from the melt pool system, in this case, InfiniIM. So first of all, we selected the information we wanted to analyze. As I said, we are only using the 3 mm specimens here. Then we had to align the coordinate system with the one from micro-CT. And then we can plot the free total volume of these emissions of the defect. We can then confine this analysis to the identified locations of the defects. Here you can see several defects are displayed in terms of 3 layers. So the layer of the defect and the ones adjacent to this layer. With this information, we can plot histograms regarding the emissions of each layer, and we can also represent the average emissions of both the layer, the defect, and other regions we define it as defect-free regions to validate our results. So we apply this approach to the keyhole sample, the one with lower scan speeds. Here we took into consideration the information from the plasma photodiode due to the nature of the emissions. So we could possibly identify some keyhole or not defects. As you can see, we have different scan track distances and directions due to the strategy we are using for printing. And this delivers different types of emissions. For instance, short vector emissions produce lower emissions, so it's a darker color here, and long scan tracks produce lower emissions, and short scan tracks result in higher emissions. This can be a problem because we have adjacent layers with different emissions, and this can mask some results and hide some defects in the emissions not properly being identified. So regarding the keyhole sample, we selected the highest defect we found, which is below the hedge distance. This can be a problem because defects may only be detected when they are comprised and have the same size of the hedge distance. Otherwise, they might be masqueraded by the neighboring emissions scan tracks. As we can see, this is the region of defect. Then we selected 2 randomly regions, and we plotted the 3 layers of the defect. As you can see, we can't distinguish between the emissions in the different layers, but we know the defect is there. This is probably the size of the defect again. Then we repeated the analysis for the optimal parameter cases, which has more defects and has a higher scanning speed. We have the same, we have the same problem because shorter scan tracks result in higher emissions, while longer scan tracks result in lower emissions. Also the same problem because we have the same scan strategy. Here we use an output photodiode because it is associated with lower emissions and might be useful to detect lower lack of vision formations. Here we have the biggest defect found was more or less 3 times the hedge distance. As we can see, here we have a slight difference from the defect region and the other normal regions chosen for this analysis, but still this is a very narrow interval of values. We still have further analysis to do, and we have to improve our methodology in order to correlate emissions with defect locations found, in this case, by microCT. So, regarding conclusions, we conclude it's evident that microCT presents a valuable tool to analyze defects such as aluminum, silicon, and magnesium alloys. A spherical criteria or criteria can also be retrieved and used based on sphericity, compactness, and aspect ratio or bounding box factor. This can be complemented with volume and diameter in order to classify the defects. Once again, this can be useful for machine learning implementation in further works. Nonetheless, melt pool monitoring systems like InfiniIM, the one we studied, may be used eventually to incorporate microCT analysis, but this is not a straightforward process and analysis, and since the emissions depend on size, position, and location of scan track factors, which affect the emissions, which can mask the defects we have. So for further works, we would like to, if you can, try different scan strategies to minimize the impact and dependence on the scan track length and directions. Also, be careful because defects higher than the hedge distance may be detected, but the others not. So we have to focus our analysis in higher defects. And different areas might also be used because in this analysis we used a fixed area to encompass the defect, but it might be probably too big and masking the defect with other emissions from adjacent scan tracks. So thank you for your presentation.